Right beneath our feet, under all the soil and forests and oceans, our planet has this hidden skeleton. Today, we're going to go on a kind of high-tech geological expedition to find it, mapping all the secret fractures and faults that really shape our world.
It's a pretty cool question, right? What if you could just peel back the surface of the Earth and see its entire underlying structure? Well, it turns out that with a powerful mix of satellite data and some seriously clever algorithms, scientists can now do pretty much exactly that.
Okay, let's get into the lingo for a sec. The key term here is geological lineament. Now, it sounds super complex, but it's really just a clue. Think of it like a faint line you might see on the Earth's surface. A strangely straight river, a little valley, or even a sudden change in the trees that hints at something much bigger, like a massive fault line hidden just underneath.
So what are these cracks in the crust, really? And, more importantly, why are we so incredibly determined to find them and map them all out?
Well, here's the thing. These lineaments are basically a treasure map. Seriously, following them can lead geologists to find valuable mineral deposits or identify these huge underground reservoirs of fresh water. They can even help us understand and get ready for potential earthquake hazards. So yeah, the stakes are incredibly high.
So how in the world do you find clues that are scattered across the entire globe? Well, you start from way up in space, scanning the whole planet with a suite of really powerful sensors.
Okay, you can think of each one of these data types as having its own unique superpower. The elevation data, that gives us a super precise 3D model of the terrain. Optical data is just like taking a really high-res photo from space. But radar, or SAR, that's the real game changer here. It's like it has X-ray vision. It lets us see the ground's actual texture right through clouds and even thick forests. It's amazing.
But just having the raw data isn't quite enough. Scientists have to process it in clever ways to make these hidden lines really pop. Imagine you have a crumpled piece of paper and you're holding a flashlight over it. As you change the angle of the light, different creases and shadows just jump out at you, right? That is exactly what they're doing digitally with the terrain data, creating these things called hillshades that reveal every single subtle line.
So with our enhanced maps all ready to go, it is time to unleash the digital detectives. We're talking about a whole suite of algorithms that are designed specifically to hunt for those hidden patterns.
So instead of just one tool, they use a whole search party. The line algorithm, that's kind of the generalist. It's great at finding all sorts of edges and curves. The Huff transform is the long-distance expert. It's looking specifically for those major continuous fault lines. And then Canny Edge Detection is the specialist for sharp contrasts, like a sudden cliff face. And by combining all of their findings, they build one master map of potential clues.
Now, you might be wondering, why go to all that trouble? Why use 3 different methods? Well, it's because no single algorithm is perfect. Each one has its own little quirks and biases. So by combining them, you get a result that's way more robust and reliable. You filter out a ton of noise, and you make sure you don't miss anything really important. But this brings us to what is, without a doubt, the most critical step in this entire process. This is the moment where artificial intelligence has to meet human intelligence.
Because for as powerful as these algorithms are, they just can't replace the brain of a trained human expert. As the researchers themselves put it, this manual review, quote, dramatically increases geological reliability. This is the step that turns a noisy computer file into a truly valid, scientifically accurate map.
And I mean, just look at the difference here. It's stunning. On the left, that's the raw computer output. It's a total mess of roads, power lines, even fences. But on the right, that's the final product. A geologist has gone through, cleaned it all up, removed all that man-made noise, and connected the dots to reveal the true underlying geological structures.
So now that we have this clean, expert-verified map of all the lineaments, the real analysis can finally begin. This is where we turn these simple lines into some profound geological insights.
Because, the individual lines are kind of like letters in an alphabet. The real story is told when we start looking for the words and the sentences, the patterns, the densities, and the orientations of the entire system. To do this, they create 3 key things. First, you've got lineament density maps. These are basically heat maps that show you which areas are the most heavily fractured. Second, intersection density maps. These highlight the hotspots where multiple faults actually cross paths, and these spots are often prime targets for finding resources. And finally, you get these beautiful rose diagrams, which are just a fantastic way to see the dominant direction that all these cracks are pointing.
And just to give you a sense of the scale we're talking about here, when they're making those density maps, analysts might use a search radius of about 5 kilometers.
So for any single point on the map, they're measuring the concentration of fractures within that area, which helps reveal these huge regional scale patterns.
And this is where it all comes together, these final maps. This is what we were after from the very beginning. They clearly show us the fault swarms, they identify zones of fractured bedrock that are perfect for holding groundwater, and they pinpoint the most promising areas to go looking for valuable minerals. We've literally turned signals from space into actionable intelligence on the ground. It really makes you think, doesn't it? By combining this incredible technology with human expertise, we're literally learning how to read the subtle clues written all over our planet's landscape. And it leaves us with one last fascinating question. What other secrets is our planet hiding, just waiting for us to find the right way to look?